All right, this is the fourth page on the big torque sheet, and we're going to do some more problems here. We've got a rod on a pivot point at W. One of the forces on it is placed 2D away, 2D, and the other was just D away from the pivot point. So this moment arm is 2D, that moment arm is D. So the question here, where would you place a third force to produce equilibrium where the sum of the torques equals 0? Let's see let's label our forces. We always try to do that. This force on the right at W, what will it cause? Will it cause a clockwise rotation or a counterclockwise rotation? This force is going to cause a counterclockwise rotation. It'll make the rod rotate this way. This one is going to create a clockwise rotation. Right now, let's compare the rotations of the two torques. We actually call counterclockwise a positive torque, so that's F. Now it's at 90 degrees, so we don't need the trig function, so it's F times 2D, that's the positive one, and the negative one is F times D, that's the clockwise torque. And so the total torque right now is F times D. So now you need in order to produce equilibrium, you need to balance out the force that we have now, which is just F times D. So you need what? You need a counterclockwise. Let's say no. You need a clockwise torque, because a clockwise torque is a negative torque. So which way would you put it? The answer is actually V or X. You could put another to balance out that F times 2D. You can put an additional F right here, right? You can add a second F, and you get your second F times D, a negative, and that would make it 0. Or you could put one right here. That's another. So this is a clockwise, a negative torque, or you could put a clockwise. Now this is clockwise also because it would go, well, it would cause it to rotate this way. So the answer is you could put it at V or you could put it at X. You could put one going up at V or one going down at V, and you can counteract that big torque at the end, the torque of 2FD, or F times 2D. That's why it's 3. So we can do it this way. So let's show it down here because we've got plenty of room. So the sum of the torques, the clockwise torque, that's that big clockwise torque. Well, that's the positive one. So the force is F, the moment arm is 2D. The negative torque, which is the clockwise, the one at V, is F times D. And how do you make that equal 0? Well, this is when you combine these two torques, or F times D. What you need to make everything 0 is a negative F times D. Negative is a clockwise torque. So you could put an additional clockwise torque at V, or you could put a clockwise torque at X. So remember, let's take a look at this clockwise. So clockwise is something that would cause the rotation to do this. So up would cause the rotation to be clockwise, and down on this side would also cause the rotation to be clockwise. Number 4, let's see what this question is. It's a frictionless pulley. It's probably a massless pulley or E2, so there's no torque. The 4 forces are exerted tangentially. They're all exerted 90 degrees. Check it out. So you don't need your trig. All of these forces are exerted 90 degrees to the axis, to the moment arm. This would be the moment arm. I don't know if you can really see this, but the bigger moment arm is 3R, and the smaller moment arm is 2R moment arm. That's from the pivot point to the force. And they're all 90 degrees. Here's a 3R. That's a big one. This is a 3R. So there are two radiuses. This is at 3R. So let's see. What's the question? What is the net force? Okay. The sum of the torques. What is the net torque? So what are the positive ones? This is clockwise, and this is counterclockwise, right? So this would be a clockwise torque. It's a negative torque. These two are counterclockwise torques. Counterclockwise torque, because it's going to make it go this way. That's a counterclockwise. This one over here is also counterclockwise. This over here is also counterclockwise. Yep. And so it looks like there's how many? There's 1, 2, 3 counterclockwise and 1 clockwise. The one up top is clockwise. That 2F with that big moment arm 3R. So let's do the positive, just like we always do. We do the positives first. So 2F times the moment arm. Take a look at the 2F. That clockwise. 2F. It's acting at 90 degrees. I don't need the trig. Times the moment arm of 3R. And then the rest of them are, whoops, I made a mistake. Whoops. Clockwise is not positive. It's counterclockwise is positive. So let's do all the counterclockwise. So this F over there is moment arm is 3R. So that's a positive F times 3R. And here's another counter at the bottom here. Another F times 3R. And the next counterclockwise, it's a shorter moment arm, only of 2R. Let me erase this so you can see it. See? So it's F times 2R. Those are all the positives. And then that big clockwise torque, which is negative, 2F times a moment arm of 3R. So it's 2F times 3R. So you got 3FR plus 3FR plus 2FR minus 6FR. So 3 plus 3 is 6, 8FR minus 6FR equals 2FR. So let's see what the question right there. What is the magnitude of the net torque of the system? Oh, I think I read this wrong. What is the net torque on this system? So that's how you do it. So it is actually 2FR. So remember, counterclockwise is positive. We call them positive torques. These first 3 were counterclockwise, and there was a single clockwise or negative torque. And then you just add up all your torques, 3FR, 3FR, 2FR, that's 8FR. 1 negative torque going the clockwise direction. 2F is the moment arm. Whoops, my bad. 3R is the moment arm. And 2F is the force. And there you go. Meter stick is of negligible mass, so small doesn't matter, on a fulcrum at the 0.6 mark. See that over here? Fulcrum is a pivot point or a balancing point right there. With a 2 kilogram mass hung at the 0 mark, and a 1 kilogram hung at the 1 meter mark. Okay. The meter stick is released from rest in a horizontal position. Immediately after it's released, the magnitude of the net torque on the system is what? Okay, net torque. So let's label this. This weight's going to go this way. So that is what? That's a counterclockwise torque. And this one will rotate. This hanging weight will make the stick want to rotate this way. This is a clockwise torque. Remember, this is anything going like this is clockwise, and anything going like, oops, did I get that right? Yeah, this is counterclockwise. And that's clockwise. Clockwise, okay. So this is going like, all right. So the net torque is what you want to find. So let's start with let's do the sum of the torques. That's tau, that's a Greek T. The positive is the counterclockwise. Now, it's force times moment arm, but we don't really have to multiply these kilograms by G because there's G on both sides and they cancel out. That's a nice little trick. Here's the moment arm. It's at the pivot, it's at 0.6. This is at the 0. So this 2 kilogram. Oh, you know what? I actually said something wrong. We do have to multiply by G because they want the net torque, and that's a Newton. So 2 times 10 gravity is 20 newtons. What's the moment arm? 0.6 is the moment arm. Meters, right? Okay. And the negative one, that is over here. This is the moment arm, 0.6 to 1. This is placed at the 1 meter mark. So the force is 10 newtons, and the moment arm is 0.4 meters because 0.6. This is at the 1 meter mark. So this is 0.6 in 1 meter. That's 0.4. So 20 times 0.6 is 12. So maybe we could do it over here. So equals 12 meter newtons minus 4 meter newtons gives you 8 meter newtons, and it's choice B. There you go. Sum of the torques. The counterclockwise is positive and the clockwise is negative. Where should you place a 4 Newton force so you can maximize the torque? Let's label these torques. Let's go over it again. This is clockwise, and this is clockwise. So what is this? This is a clockwise torque. This will make the box rotate clockwise. This is also clockwise, and this is counterclockwise. Is that the most? Now there are angles here. Will that give us the maximum torque? Let's check the other one. This is going to counterclockwise because it's going to make it rotate this way. This is also counterclockwise, and this is clockwise. So this is all these unlabeled. This is supposed. Should you place the 4 Newton here to max, or do you place it here, or do you place it here? You know what I could do? Automatically cancel out. Do you realize since this 4 Newton force is applied right through the pivot point, it provides no torque at all? Notice this. This will not rotate the box if it's applied through the pivot point. So I can cross out these two choices. So which one is it? Which one's going to maximize the torque? Well, let's take a look. The answer is B. Why? Because the 4 joins with the 8. The 4 forms a 12 Newton. Well, it's not really 12 newtons because we have an angle here, but certainly the 8, this 4, they all have the same moment arm. We don't know what it is, so that's the same. And they all have the same angle, so that cancels out. The 4 and the 8, this is the maximum. If you place the 4 here, you'll get the maximum torque because the 4 will join with the 8. Over here, the 4, this actually torque is probably 0. The two clockwise torques of 4 and 4 this torque will be 0 because the two 4 Newton clockwise forces will be canceled out by the 8 Newton counterclockwise. So it's B. Where should another 4 Newton force be applied to create equilibrium? And I think we just figured that one out. That's this guy right here. Because if you place the 4 Newton here, it'll be a what? Let's take a look. It'll be a clockwise torque, and another 4 Newton clockwise torque will match the counterclockwise torque. So there's where 0. 2 wheels are fixed on each other. We've got a lot of different radiuses. What's the net torque? Okay, so let's do the positive first. Let's first label these. Remember, this is, the needle of the second hand of a clock goes like this. This is clockwise. So that's clockwise and clockwise and clockwise and counterclockwise. It's going to cause it to rotate counterclockwise. So that's the positive force. Now it says the magnitude of the net torque. So even if we get negative, we're going to report it as positive. So let's do the counterclockwise. That's F times a radius of 2r. So that's the biggest. So F times 2r, the force times the moment arm. And notice all of these forces are perpendicular to the moment arm. Let me show you what I mean. Look at this force over here. It's applied here. And look, it's perpendicular to the moment arm. So I don't need sine just yet. This is also perpendicular to the moment arm. Well, there we go, like that. Okay, so the counterclockwise is f times 2r. Then you've got this one over here. This guy right here is just 2f times, let me clean it up so I can see. Yeah, 2f times r. That's another counterclockwise. And the other, whoops, this is, wait a second, my bad. There's only one counterclockwise. The rest are all clockwise. This is clockwise. So 2f times r minus, here's another one, this f right here, so it's a negative, so minus f times 2r. It's minus the last one, f times the other big moment arm, say, right there, f times 2r. So 2fr minus 2fr minus 2fr minus 2fr. Let's see if we get the answer. So that's 2 minus 2, 4, 6, 2f, oh good, 2fr minus 6fr equals negative 4fr. Why is there no negative choice? Because it's magnitude. Magnitude, because the question asks for magnitude, that just means size. You don't need the direction of the torque. I think we'll make this one the last one. You've got a torque here at 90 degrees, so we don't need the trig. What is the torque? Here's the pivot, and the length is L, so that's the torque. Which one of these which one of these choices actually are the same torque? Let's say equal in magnitude to that torque. Let's see. This one would be, now we haven't done a lot of trig, but this one would be 2f sine 120. Now it's no longer 90, so we have to include the angle times L. Oops, it's a lowercase l. Okay, this one is L is 2f times sine of 60 times L, 3f. Now that's 90, so I don't need the trig, but it looks like L over 2. This one here is 2f sine of 30 times L, and check it out, I think we've got the answer because sine of 30 is a half. This is f times L, that's why it's D, and that's it for this. We'll stop at 5.